You know, we all love the equals sign, right? It's clean, it's simple, it gives us one perfect answer. But let's be real, the world is way messier than that. It's full of phrases like at least, no more than, or somewhere in between. So how on earth do we use math to describe a world that isn't always so exact? Well, that's exactly what we're going to dive into today by exploring the super powerful tools of inequalities and systems of equations.
Right? I mean, think about your own life. You have a budget for the month, a limit you can't go over, or maybe you're baking and the recipe calls for at least 2 cups of flour. The real world is built on these kinds of conditions and ranges, not just perfect, neat, equal signs. So math needs some tools to deal with all this fuzziness, and that's where our journey really kicks off.
Okay, so our first building block here is to get a handle on the main tool for describing these relationships, the inequality. Let's break down what that actually is.
An inequality, or bu등식, as our source material calls it, is really just a statement that two things aren't equal. Simple as that. Instead of one equal sign, we get this awesome team of 4 symbols: greater than, less than, and then their cousins, greater than or equal to, and less than or equal to. These little symbols are what let us stop searching for one tiny dot on a map and start defining entire regions of possibilities. But here's the thing. You can't just treat these symbols like a regular old equal sign. Oh no. Inequalities have their own special set of rules, properties that tell us exactly what we can and can't do. And believe me, understanding these rules is absolutely crucial if you want to get the right answer. Now, the first 2 rules, super easy. They act just like you'd expect. You can add or subtract whatever you want, multiply by a positive number, and that inequality sign stays put. It doesn't budge. But that third rule, oh, that's the big one. That's the game changer. The second a negative number gets involved in multiplication or division, the whole logic of the statement flips on its head. Let's actually see this in action, because it can feel a little weird at first. I think we can all agree that 3 is greater than 2. It's a simple, undeniable fact. Okay, so what happens if we take both sides and multiply them by -1? All of a sudden, we're comparing -3 and -2. Just picture a number line in your head. Which one of those is actually bigger, further to the right? The whole relationship just got turned upside down, didn't it? And there it is. This is the perfect illustration of that rule. To keep the statement true, the sign has to flip. -3 is now less than -2. This is the one thing you have to remember, the absolute core property that makes inequalities so unique. All right, now that we've got that critical rule locked in our minds, let's put it to the test and actually solve our first linear inequality. Okay, let's tackle this thing. So step 1 feels familiar, just like a regular equation. We want to get all the variables on one side and all the numbers on the other. That simplifies down nicely to -5x is greater than -10. And here we go. This is the moment of truth. To get x all by itself, we have to divide by -5. That's the trigger. The alarm bell should be going off. We have to flip that sign. So our final answer isn't that x is greater than 2, it's that x is less than 2. See? That one single rule makes all the difference in the world. So, we're getting pretty good at handling one relationship at a time. But what happens when a problem has more than one condition and they all have to be true at the same time? We need a single answer that solves 2 different equations. That's when we need what's called a system of equations. Now, to find that one golden ticket answer that works for both equations, we've got 2 main strategies. First up is substitution, or 대입법. This is your go-to move when one of the equations pretty much hands you the answer, like y equals x plus 2. The second method is elimination, or 가감법. This one's more like a clever magic trick where you line up the equations just right to make one of the variables completely disappear. Let's give substitution a try first. See that top equation? It's basically handing us the value of y on a silver platter. So we take that information, x plus 2, and we literally plug it into the second equation right where the y is. The magic here is that, poof, we've created a brand new equation that only has one variable, x, and that's super easy to solve. We find out x equals 2, and from there, we just pop that value right back into that first equation to find that y must be 4. See? It's like a domino effect. All right, now for elimination. The goal here is totally different. We want to engineer a situation where one of the variables just cancels itself out. Look here, we've got a plus 2y in the first equation and a minus y in the second. They're so close to being perfect opposites. So what if we just multiply that entire second equation by 2?
We get a perfect match, a plus 2y and a minus 2y. Now, when we add the two equations together, the y terms are eliminated. They just vanish, leaving us with a simple equation that tells us x equals 2. And just like before, we plug that back in to find y.
But what if you follow all the rules perfectly and something just weird happens? Sometimes a system of equations has a little secret. It's impossible to solve. Let's see what that actually looks like. Okay, so let's try to solve this system using our elimination trick. We'll multiply that first equation by 2 so the coefficients match up. Now, just take a second and look really closely at what we've got. Do you see the problem here? The entire left side of both equations is now identical. And that is just a complete logical contradiction. It makes no sense. We've basically created a statement that says the exact same thing, 4x plus 2y, is equal to -6 and +6 at the very same time. That's impossible. There's no combination of x and y in the universe that can make that true. And that's our clue. This system has no solution.
Now let's look at the other special case. What happens if, instead of hitting a brick wall with a contradiction, we find something that's just, well, repetitive?
We're going to use the exact same strategy as before. Let's multiply that top equation by 2 to try and make things match up. But watch what happens this time. Take a good look at the results. They're identical. We never really had two different equations to begin with. We just had the same equation wearing a clever disguise. What this means is that any solution that works for the first equation is guaranteed to work for the second one because they're the same line. They share all of their points, which means this system has infinite solutions. So let's just quickly boil all of that down. When it comes to inequalities, the number one golden most important rule is flip that sign when you multiply or divide by a negative number. For systems of equations, your two main weapons are substitution and elimination. And finally, always keep an eye out for those tricky special cases, the impossible contradiction that means no solution, and the hidden twin that means infinite solutions.
And really, that brings us to the big picture. I know these can feel like abstract rules for a math class, but they're honestly the foundation for solving some incredibly complex, real-world problems. Everything from engineering challenges to economic models. They give us a language to define not just what is, but what is possible. What else could we understand if we master them? Thanks for watching.